Okay, what we have here is our first foray into differential equations. A differential equation is an equation that has a derivative in it. Now, sometimes we'll write this in differential form. Sometimes we'll say y prime. So what we're going to be given here is a derivative, an equation that has a derivative in it. I want to find the function that satisfies that equation. The solution to a differential equation is not a number. We're not trying to get x equals 7. We're trying to get y equals some function of x. And that'd be some function that satisfies the differential equation. Now we know that if two functions differ by a constant, then they have the same derivative. So typically speaking, differential equations have an infinite number of answers. What we'll do to narrow down the particular solution that we want is solve what's called an initial value problem, where we're told, okay, you get your solution, it's going to have a plus c in it. Now I want you to solve for c using some predetermined value. So we've got here, this is a differential equation. It's a very simple one. The derivative of the function we're looking for is sine. So y prime is sine of x. Or in other words, dy dx is sine of x. Now we could just think about this for a minute. Whose derivative is sine? It's negative cosine. It's not regular cosine, because the derivative of regular cosine would be negative sine, and I ain't got a negative. Let's solve this using integrals. So I'm going to take the integral dx of both sides. I'm getting kind of advanced on my notation here. The antiderivative of dy dx, you could think of it this way, that the dx's kind of cancel. The dx is not actually an algebraic quantity. It doesn't really cancel. What we're really using here is chain rule, but we could pretend like the dx's cancel here, leaving, instead of dy over dx times dx, just dy. The antiderivative of dy, see, now I have a different differential in here. That's why it's important that you always write your differentials. The antiderivative of dy is just y. The antiderivative of sine of x is negative cosine of x plus c. So we kind of figured this out ahead of time. I'm looking for some function whose derivative is sine of x. That's negative cosine of x. Now I want to satisfy this initial value. So this right here is really y of x. Remember, y is a function of x here. I'm going to make all this a little smaller so I can fit everything in here. Okay, so this is really y of x is negative cosine of x plus c. I want y of 0, which would be negative cosine of 0 plus c to equal 5. Now I want to solve this for c. What's cosine of 0? Cosine of 0 is 1. So that's negative 1 plus c equals 5. So c will equal 6. So then my particular solution to this initial value problem, we call that an IVP, is y of x equals negative cosine of x plus 6. This is an entire family of solutions. Any value you pick for c, make up a number. It's a solution to this differential equation. There's only one solution that passes through the point 0.05, and that's when c equals 6. Okay, let's do this problem. This will be our last problem today. So we've got a car traveling at some rate. So we know my initial velocity, v of 0, is 88 feet per second. That's my initial velocity. I'm also told that I'm decelerating. I hate that word, by the way. That's not a real physics word. In your physics class, you will not use the word decelerating. You'll say you're accelerating at a negative rate. When you're slowing down, we're not going to use the word decelerating. Our acceleration is negative in this particular case. So my acceleration is just a constant of negative 15 feet per second squared. I want to know how many seconds elapses until the car stops. Okay. So what I'm going to do is I'm going to solve for v of t, because we know that the acceleration is the derivative of velocity. Therefore, velocity is the antiderivative of acceleration, dt. Don't forget your dt there. So v of t will be the antiderivative of negative 15 dt. You'll never write an integral without writing a differential here. The antiderivative of a constant, you just pick up your variable. What's my variable in this case? T plus c. Don't forget your plus c. Now I have this initial value here. That's the point 0.88. So I'm told v of 0 equals 88. But what is v of 0? That would be negative 15 times 0 plus c. So c equals 88. That tells me my particular solution will be negative 15t plus 88. Okay. Now I can figure out how long does it take until the car stops. What's your velocity when the car stops? Now I want to actually solve something. I want to solve 4 times. Solve v equals 0. So negative 15t plus 88 equals 0. We could see pretty quickly you get 88 over 15 seconds. And here we'll throw that in our fancy calculator. Let me pause. That is 5.87 seconds. That's how long it takes until the velocity has reached 0. See, we're starting off, there's my initial velocity, and I'm losing 15 feet per second every second. That's when an acceleration is. So it takes almost 6 seconds to come to a stop. Now let's figure out how far the car travels. We know that velocity is the derivative of position. The derivative with respect to time of position. Position here, I'm going to call x because we're moving, horizontally here. We're not moving up and down. I wouldn't want to call it y, x of t. So my position, I'm going to call x. I know the derivative of position is velocity, so hence position is the antiderivative of velocity. So that will be the antiderivative of negative 15t plus 88 dt. Don't forget your differential in here. You'll never in your life have an integral symbol without a differential inside here. On a test, every time you leave that off, it's a -1. Okay, let's take the antiderivative here. Okay, the -15 comes along for the ride. Antiderivative with respect to t of t, that's t to the first, right? So that exponent's going to go up by 1, divide by the new exponent. Antiderivative of a constant, you just pick up your variable. Think backwards here. If I'm taking this guy's derivative, what's the derivative of 88t with respect to t? 88 plus c. Now, I'm not looking for like a new position. I'm looking for change in position, right? A couple of ways to think about this. So I had my car here. Here's my car. He's moving along. He's going 88 feet per second, and he starts to slow down. He's going to end up over here at some final position. We could call this some initial position here. And the acceleration, he's slowing down. Acceleration will point in the opposite direction, -15 feet per second squared. What I'm looking for is this distance here. I can call my initial position whatever I want. I could say my initial position was 1,000 feet. And then if this is 1,020, then the change in position, the distance, would be 20. Or for simplicity, since this happens at t equals 0, I might as well call my initial position 0. That's when I started my clock. Right here, I started my clock at that spot, and I'm naming that x equals 0. This is what I want. I know that occurs when t equals, what we get? 5.87 seconds. And that happens to be when v equals 0. Okay, so all I'm doing here, I know the time, just plug in. X of 5.87 would be -15 times 5.87 squared over 2 plus 88 times 5.87 plus, oh, we need to solve for c. Should have done that first. I chose x of 0 equals 0. That's at time 0. So now we can just plug in 0 plus 0 plus c. I get c equals 0. So I got to choose this. All right, and now here, let me pause and I'll figure out what that is. Okay, so I plugged all this in and I got x after 5.87 seconds is 258.13 feet. Okay, so that's how far we went. This is a great physics problem. In your second week of physics, which you'll probably take next semester, you're going to be doing problems just like this. So we're going to do several like this semester. Okay, that's a good place to stop there.